Today I'd like to take a look back at 10 years of Lidar operations at the NOAA Fritz Peak Observatory. Slide 2 here gives you a little background information about the observatory itself. The building, which is pictured here on the lower left, is located about 25 miles from Boulder in the Colorado Mountains at an elevation of almost 9,000 feet. And despite its institutional appearance, this building was actually built in the late 1940s as a mountain lodge and restaurant. During the 1950s, Franklin Roach approached the owners of the building and asked whether he might be able to build this platform, shown here on the lower right, on top of Fritz Peak, which is located right behind the observatory building, in order to measure the ionospheric air glow, and he started those measurements during the International Geophysical Year, 1957. In 1965, the National Bureau of Standards, now NIST of course, purchased the building so that scientists could stay there overnight and also to use, of course, the facilities for other experiments. And in 1970, the NOAA Astronomy Lab, recently created, assumed control of the building. And during the 70s, John Noxon, who was director of the observatory, made his first spectroscopic measurements of column NO2 in the troposphere and stratosphere. And during the 1980s and 90s, there were quite a few other experiments located there at the observatory, including some that were part of the network for detection of stratospheric change. Most of the operations at the observatory ceased after 1999, and the building was actually donated to the Timberline Fire Protection District just a couple of months ago after several years of negotiations. Slide 3 talks about the beginnings of the tropospheric ozone LIDAR program at Fritz Peak, and this was the brainchild of Mike Profit, who wanted to characterize the trends in upper tropospheric ozone as part of NOAA's new radially important trace gas, or RITS, initiative. And the design was inspired by the system developed by Brouwer at NASA and Pellan-Mégy in France, and used two YAG pump dye lasers to optimize the wavelengths for daytime measurements into the lower stratosphere. So Mike came up with a basic design for the LIDAR. He configured a lab space there at Fritz Peak and purchased many of the major components, including the digitizers and the lasers. But as many of you know, Mike's attention was diverted by the Antarctic ozone hole and his critical role as PI of the ozone photometer that flew aboard the ER-2. And given the distractions associated with the measurements over the next few years, both in the Antarctic and Arctic, the development of the LIDAR at Fritz Peak was put on pause. I joined the project in 1990 and spent the next few years completing the system with Tim O'Leary and Chris Masters. A number of technical hurdles needed to be overcome associated with laser timing, signal-induced bias, and digitizer nonlinearities, things many of you are familiar with. We described the system in a paper in Applied Optics in 1997, and here are the schematics from that paper showing the basic configuration here. As I mentioned before, we used two YAG pump dye lasers to generate frequency double wavelengths between 286 and 292 nanometers. And these two lasers were fired sequentially about 400 microseconds apart. And we used a nickel sulfide filter for solar blind operation. This transmitted those wavelengths from 286 to 292 with a hard cutoff at 292 so that we could use one photomultiplier tube to detect all of the signals. We duplicated this detection chain in a near and far range detection channels, with the far range having a 61 centimeter or 24-inch telescope. And with this configuration, we could operate during the day from about 1 kilometer above the surface, or 4 kilometers ASL, to about 12 kilometers ASL into the lowermost stratosphere. With a 2 to 10 minute iteration times, we could achieve 10% accuracy with a 1 kilometer range gates. there was a separate 532 nanometer aerosol channel that used about a watt of the leftover green light and a Daystar filter, so it could also operate up into the stratosphere during the daytime. Mike wanted to call the system the Rapidly Tunable Daylight Differential Absorption Lidar, or the RTD dial, in part because RTD was the same as our local bus service, Regional Transportation District. And I guess that's appropriate because the system was as large as a city bus. Fortunately, we had enough room within the laboratory there at Fritz Peak that size wasn't a consideration. We weren't trying to put this system into an aircraft or into a trailer. Figure slide 5 here. And Mount Pinatubo, as we know, injected about 15 megatons of SO2 into the stratosphere and created a sulfate layer that circled the globe and spread to mid-latitudes. And we realized we could remove that solar blind filter and measure this aerosol backscatter, both using the 532 from one laser and then a dye laser wavelength from the second laser. To measure the backscatter, 2 different wavelengths. And we did this over 120 nights over the next 2 years. The evolution of that backscatter is seen in the contour plot on the right there. And we also figured out we could tune that dye laser to 589 nanometers and profile the resonance fluorescence from the mesospheric sodium layer at around 100 kilometers. And we could do this with analog detection with that 24-inch telescope and, of course, lots of power in the dye laser. Along the way to building up that database of upper tropospheric ozone, we did lots of measurements and saw a lot of interesting things, some of which are summarized in the next few slides. Slide 6 shows some examples of stratosphere-troposphere exchange, which we measured over a number of years. Lots of examples, 2 of which are shown here in the first 2 panels of this plot, both a longitudinal and a transverse cross-sections through tropopause folds. We also saw quasi-horizontal stratospheric streamers, which are created by anticyclonic intrusions. And the final figure here, shown down in C from May of 1999, during the last full month of operation of the system, we directly show that stratospheric intrusions could cause an exceedance of the U.S. National Ambient Air Quality Standard, actually the 85 ppb standard, which was in effect at that time. And this definitive measurement kind of settled what had been a contentious argument for a number of years as to just how important stratospheric intrusions were in terms of surface concentrations and whether they really could cause exceedances of the NACs. We also discovered that not all of these downward sloping tongues that we saw in our time height curtain plots were caused by tropopause folds, that some in fact were caused by inertia gravity waves. And here's an example from some measurements. There's a 14-hour curtain plot there on the left showing these downward sloping bands of enhanced ozone. And basically, if you have a gradient in ozone or any other tracer, which of course you do, going from the troposphere into the stratosphere, then the vertical motions associated with these inertia gravity waves, which have a vertical wavelength on the order of a few kilometers, can create fluctuations, such as those are shown in the top panel in the middle of the slide here. These are just a couple of profiles that were taken several hours apart, and you can see they're almost out of phase fluctuations. These particular fluctuations were caused by a gravity wave, inertia gravity wave, with a horizontal wavelength of about 180 kilometers and vertical wavelength of 3 kilometers. There's measurements on the left in the curtain plot, and then a simulation on the right showing how you could get these downward sloping tongues. The observations also show there within the dotted circle a discontinuity in the tongues, which was caused by breaking of the inertia gravity wave at the tropopause, at the inversion, and this actually caused some stratosphere-troposphere exchange, which Jean-Francois Lamarck described in a paper in 1996. The final slide here summarizes the 6 years of measurements we made with the RTD-DAL system at Fritz Peak. We acquired more than 25,000 ozone profiles between June of 1993 and June of 1999. The middle and upper tropospheric parts of those measurements are summarized in the curtain plot on the left. And you can see that there's quite a bit of an interannual variability in the ozone. You see higher concentrations in 1995 and 1998. And if you take a slice through this curtain plot, for example, 9 kilometers, shown here with a white line, you can create a time series such as plotted here on the right. And the filled black circles show the ozone measurements, monthly ozone measurements over this period. And you can see that there are year-to-year fluctuations on the order of 10 parts per billion, really quite substantial. I've also plotted here the 200 hectopascal wind speeds from the Pacific Ocean off the coast of North America. And what we discovered in our analyses was that this interannual variability was created by ENSO, which moved around the position of the subtropical jet. And so we're seeing the effects of more or less continuous, quasi-continuous stratosphere-troposphere exchange around the subtropical jet, changing the concentrations in the upper troposphere here. And we found that these fluctuations are so large that in order to determine robust trends, we would need at least 15 years of measurements at Fritz Peak or really any other site in the southwestern US which is affected by this phenomenon. Unfortunately, this requirement did not fit with the timescale of the project and ultimately led to the termination of the project. We were able to write quite a few publications based on this short 6-year record of measurements. I've summarized those in the next few slides. I won't go into them to detail. You can look at them at your leisure. But a lot of interesting science came out of this project, which unfortunately was ended much too soon. Thanks for your attention.